Aya Berhala, Aya Serabi, Aya Serabi, not here. Al Mohammed Lemo, Lemo, Al Shaban Abdallah, Abdallah is not here. Amro Habiba, Shabda Biyai, Barak Rama, Ganfan Beatrice, Young VIM, Kampire Yasmin, Katz Adil, Levi Gali, Mahbub Mariam, Mohammadi Abu Taleb, Murata Hatsun, Naiga Kevin, Nishimura Shikibu, Okeke Indrani, Patel Krish, Reinbergenov Asadbek, Sansu Chan Miai. Oh, keep on changing your location. Shemiria, Unuma Misaki, not here. Fan Ivan Yakov, Sama Bashar, and then other group. What is the other group now? 9. 9. Okay. Show Aro. In the meantime, students are escaping. Wang Yeon Seo, Isogai Risa, Kim Gayon, Makwana Kumari, Marais Johannes, Mahmoud Hiba, Muslimi Remata, Maluk Wago Hadiyak, Okpara Isabella, Tittapilil Chelsea, Rotman Fairos, Saad Omer Mabdi, Sharuba Tarifuka, Sayek Walid, Yasukochi Takaki, Mulungi Isabel, Yasmin. Okay. Everybody could hear his or her name. Fantastic. So, my recollection is that we couldn't complete this thymus. Actually, we couldn't even start it, right? So let's start with that. This is still the previous seminar's material, 27. As you can read, it is called thymus lymphaticus, which refers to one particular stage of development of the thymus. So we need to talk about the development of the thymus. There are 3 stages of its development. The first one is called thymus epithelialis. This is basically during intrauterine life. Then in childhood, the stage is thymus lymphaticus. This is what we have in our section. And after childhood, so later during life, the stage is called thymus adiposus. So what all that means. The stroma of the thymus is given by epithelio-reticular cells, special kind of cells with processes. This gives the stroma. And this is unusual because usually the stroma of organs is given by reticular fibers and reticular cells. But the thymus is an exception. And the other thing, the origin of the stroma, because the origin of the stroma of the thymus, so the origin of epithelio-reticular cells, is the third pharyngeal pouch, so it is endodermal, third pharyngeal pouch. While in other organs, including other lymphatic organs, the stroma is from the mesoderm. Okay, so different term later. During development of the thymus, first the stroma appears, and as we said, it is given by epithelio-reticular cells. That's why this stage, so the stage when lymphatic tissue is still not present, this first stage is called thymus or thymus epithelialis, referring to the epithelio-reticular cells. Later, in early childhood, lymphocytes, mostly T lymphocytes, invade the stroma. And here you can see this bluish looking tissue, which is most of the section. Bluish is the many cell nuclei, most of which are T lymphocytes. So the thymus, when it is in the stage of being thymus lymphaticus, like here, it is T dependent entirely, T dependent. And there is a minority of white adipose tissue, as you can see here or there, and even in the middle of the parenchyma. Some little areas are filled with white adipose tissue cells, but that's the minority. So that's why we can state that this is the thymus lymphaticus. Later on, during life, the amount of lymphatic tissue regresses. This is after childhood. And gradually, more and more part of the tissue will be given by white adipose tissue. And when the white adipose tissue dominates in older age, then this stage is called thymus adiposus. We don't have section from the first and last stages. We have just this thymus lymphaticus, which means this sample was taken from a child. So that's the background. The thymus has 2 lobes and surrounded by a connective tissue capsule, which is visible here. And from the capsule, connective tissue trabecules arise and divide the parenchyma into kind of lobules, kind of units. lobules. But these lobules are not separated completely from one another. This is just an incomplete separation by the connective tissue trabeculus. The other thing what we can observe that there are more and less basophilic or darker and paler bluish territories. And in certain territories this is very much look like lymphatic nodule, but that's a wrong impression. No lymphatic nodule in the thymus at all. So here the darker territories are called cortex, the paler territories are called medulla. And in each lobule we have a cortical portion and a medullary portion. Okay, so no follicle, because follicles are independent as we already discussed that the whole thymus is T-dependent. Now, another unique feature of the thymus is the presence of these structures in the medulla, like this, or like that, or like that. These are Hassall's corpuscles, capital H and double S. Inside, Hassall's corpuscles. These are always in the medulla, and these structures are present only in the thymus. These Hassall's corpuscles are basically given by partly or totally keratinized epithelio-reticular cells. And what we know about their function is that these structures produce hormones. Probably epithelio-reticular cells at other locations in the thymus also produce hormones, so multiple hormones are produced in the thymus. And one major effect of these hormones is to affect development and maturation of T lymphocytes here. T lymphocytes, when they are located in the thymus, they are also called thymocytes. So thymic hormones affect differentiation of thymocytes, if you want to put it in a very nice way. Actually, there are 6 different types of epithelio-reticular cells. We don't teach the details. One type contributes to the Hassall's corpuscle. 3 types are in the cortex. 3 other types are in the medulla. Another thing that certain types, but not all types of epithelio-reticular cells are professional antigen presenting cells, so they have MHC2 molecules. Okay. So we need to discuss what happens actually in the thymic parenchyma to the T lymphocytes. Being this is a primary lymphatic organ, we can say that, of course, antigen-independent differentiation, maturation, selection, education, whatever you like, is going on for the T lymphocytes. So, more specifically, when thymus epithelialis already developed, naive T lymphocytes arrive and invade this thymus epithelialis. Naive means here that T lymphocytes which haven't encountered an antigen. Okay? Naive. How can they arrive here? Well, definitely with blood. They cannot arrive with lymph because there is no afferent lymphatic vessel to the thymus. There are efferent lymphatic vessels, so vessels which which conduct lymph away from the thymus, but there is no lymphatic vessel which brings lymph to the thymus. Okay? But of course, blood is coming in. So T lymphocytes come with blood, although there is no HEV in the thymus. So, but instead, there are special vessels at the border of cortex and medulla where T lymphocytes may leave blood circulation and enter the parenchyma. Okay, but these are not HEVs, not high endothelial venules, because they are not present here. So this way, naive T lymphocytes invade the stroma. And these thymocytes, we can already call them thymocytes, undergo a two-step selection or a two-step examination, if you like. And this exam is quite hard. And if the T lymphocyte fails, the punishment is hard, because the punishment is death. So how is this exam? The first step is in the cortex, and this step is called positive selection. Positive selection. It is called positive because the correct answer, which is expected from the T lymphocyte, is yes. So what is the question? The question is whether or not the T lymphocyte can recognize the MHC molecule with high affinity. And they have to. Otherwise they die by apoptosis and will be phagocytosed by macrophages. So this is the positive selection. They need to be able to recognize the MHC molecule. MHC molecules are around because, as I said, certain kinds of epithelial reticular cells have MHC, 2 molecules, and all kinds have MHC1. In addition, macrophages also have both kinds of MHC. Okay? And in addition, probably dendritic cells, but not the follicular dendritic cells, but the interdigitating dendritic cells are also around, which are also professional antigen presenting cells, having MHC1 and MHC2 as well. So MHCs are around. Now, if the lymphocyte can recognize the MHC with high affinity, it will go to the medulla, where the next step of the exam goes on, which is the so-called negative selection. And it is called negative because the expected answer from the lymphocyte is no. And the question is whether or not the T lymphocyte can recognize the self-antigen. Self-antigen. So certain descriptions say that in the thymus we only have self-antigens, no foreign antigen is present inside the parenchyma. And the T lymphocyte mustn't recognize these self-antigens. If they do, they die via apoptosis and phagocytosed by macrophages. So only those lymphocytes can survive in the thymus which cannot recognize the self-antigen but can recognize the MHC. These may leave the thymus. So it is very crucial that T lymphocytes which can recognize self-antigens die. The reason is, if they don't die, if they survive, then they could attack self cells. with the self-antigens on the surface. So this failure would lead to an autoimmune disease when the immune system attacks self-cells. So that's why it is crucial to eliminate the lymphocytes which could do this. Descriptions say that something like 95% of lymphocytes die because they fail certain phases in this exam. So the success rate is about 5%. So compared to the final exam in anatomy, histology and embryology, we are still better off because in our department the success rate is much higher than 5%. And the other thing, the punishment if you fail is far from being death. We just invite you back for another round, okay? So just to make it, to put it into context, okay? So this is not a hostile environment, but the thymus is for the T lymphocyte. Okay, so there is something else what we need to discuss in relation to this. So because there is no incoming lymph, antigens cannot come to the thymus through lymphatic circulation. So antigens can come only through blood circulation. And therefore, there is a barrier called blood-thymus barrier around capillaries in the thymus. And this barrier, this blood-thymus barrier, has the function to select among antigens which can and which cannot go through the barrier from blood to the parenchyma of the thymus. And this barrier assures that only self-antigens be present in the thymus, okay? Foreign antigens are not allowed to go through the barrier. So all this makes sense, okay? And interrelated. So we need to discuss the tissue layers of this barrier. Well, if you ask me to show the barrier, I'm in trouble because this is an electron microscopic structure. In the handout, we carefully selected something which is more like, looks like a barrier, but well, so first of all, before going to the barrier, I'm showing this nucleus to you. This is probably an epithelio-reticular cell nucleus, which has a pale, relatively large, compared to the size of the lymphocytes, and have euchromatic nucleus. And the cytoplasm of this cell is pale stained, and the cytoplasm has processes, as you can see more or less. So this is an epithelio-reticular cell, how it appears. And usually lymphocytes surround these epithelio-reticular cells because they test themselves whether or not they can recognize MHC or antigen. Now, the other thing nearby, well, it's not a very nice example, but look at this kind of longitudinal view, which is probably a capillary. This is probably an endothelial cell nucleus, heterochromatic squamous. The lumen is not quite visible, but should be somewhere here. And look at these pale euchromatic nuclei, little bit elongated. These are probably epithelio-reticular cells. So this is where the barrier is, but I cannot show all layers because the barrier consists of 5 layers. So if we start from the lumen of the capillary, the first layer is the endothelium. The next layer, the basal lamina of the endothelium. Then we have a connective tissue around the vessel, therefore it is called perivascular connective tissue. Perivascular connective tissue, which has macrophages inside. I cannot show. Then we have another basal lamina which belongs to the epithelio-reticular cells. And the final layer is the epithelio-reticular cell layer itself. So we have two cellular layers, two basal laminae, and between the two basal laminae we have connective tissue with macrophages, right? Now this barrier is responsible for selection of antigens which are allowed to go into the parenchyma from bloodstream. Basically only self-antigens are allowed to enter the parenchyma. And macrophages make sure for this, if some foreign antigens enter, then those macrophages can phagocyte those down. Okay? So we have this blood thymus barrier, plus we have no afferent lymphatic vessels. So that's why these two facts assures the foreign antigen-free environment inside the parenchyma of the thymus. All right? Does it make sense? Yes.
So which antigens go in? So which antigens go in?
In the thymus, only self-antigens are present. Self. So basically those kind of protein molecules which are made by self cells. Because remember, all the proteins which are made by the self cells are inserted into the cytoplasmic membrane of that cell in the vicinity of the MHC1 molecule. So all cells show the identity for other cells. Okay, so this is the thymus. Any question? Yeah.
How to distinguish between the dendritic cells and the epithelial?
That's a good question, because they look the same in the light microscopic level. You cannot. But probably most of the cells which looking like that I showed, most of them are epithelio-reticular cells. Okay, anything else? If not, then let's continue. And let's continue with the tonsils. We have two tonsils here, palatine tonsil and lingual tonsil. I'm going to open both because we need to compare them. So tonsils are secondary lymphatic organs. As such, antigen-dependent maturation of lymphocytes is the major function. And this is supported by the build-up, the histological build-up of tonsils and the histological build-up of all secondary lymphatic organs. And this build-up assures to increase chances for lymphocytes to meet antigens. This is the purpose of being in a secondary lymphatic organ for the lymphocytes, to have a high probability to meet antigens. Okay? So here on the left side you can see the lingual tonsil, right side is the palatine tonsil. So how can you distinguish them? We don't have sections from any other tonsil. So how to distinguish these two? First of all, look at this bluish looking tissue. Bluish looking tissue is lymphatic tissue because the tint of bluish color is given by the many lymphocyte nuclei. And this lymphatic tissue here is relatively small compared to the total tissue mass seen in the section, because this more considerable part of the tissue here in the section, this is the tissue of the tongue. Now look at the palatine tonsil. Here the bluish tissue is giving the majority of the tissue seen in the section. Okay? So this is a definite difference. Another difference, if you look at these more or less empty looking structures, here, also here, these are crypts, kind of blindly ending sacs which communicate with the oral cavity. But the other end is a dead end. So it's a blind pouch. Which means that in the lumen of these crypts, the saliva and its all components, including pathogens, may be present. Because these crypts open freely to the oral cavity. Well, these openings are usually not visible because they are not in the plane of sectioning. But for example, look at here, you can see the communication, because this territory is the oral cavity and it communicates with the lumen of the crypt, here, also here. Here you can also see this interconnection because this is the oral cavity. So you can see the direct connection here, but you cannot see here. But it also has, but the connection is not seen in the plane of sectioning, that's all. So let's compare the morphology of these crypts in the palatine tonsil and the lingual tonsil. There are two major differences in the morphology of these crypts. First of all, crypts in the palatine tonsil are deeper relative to the lingual tonsil. So the magnification is not equal, but I try to. Oh, I cannot. Why? Can I change it? Why? Oh, okay. Maybe I can. So 2000 micrometer, 2000 micrometer. So now you can validly compare the size. So these are longer crypts here in the palatine tonsil, deeper. The other difference that the crypts are more branchy in the palatine tonsil. Okay. So these two differences in the morphology of crypts can, at least partly, explain the differences in the frequency of inflammation in these two tonsils. Palatine tonsil has a much higher tendency to get inflamed. When we are talking about tonsillitis, meaning the inflammation of the tonsil, we mean the inflammation of the palatine tonsil. So tonsil in most cases in everyday practice means palatine tonsil because it has the highest tendency of inflammation. So why? Because bacteria, which naturally present in the saliva, in the oral cavity, can go into the crypt. And because crypts in the palatine tonsil are very branchy and deep, at the dead end of these crypts, the bacteria, pathogens, can proliferate without too much disturbance. They cannot be washed away, okay, easily. So they can cause inflammation. This is much less likely in the shallower and less branchy crypts of the lingual tonsil. So the difference in frequency of inflammation is very much related to differences in the morphology of crypts, right? But there is another difference, because here in the vicinity of the lingual tonsil we have these glands, which are embedded, mucous glands embedded into the tissue of the tongue. And these glands have ducts, of course, like here or like there, here or here. And these ducts, you cannot follow them continuously because they are a little bit curvy relative to the plane of sectioning. But it is quite clear that they are converging towards the tonsils. And they may open into the crypt. Not all of them, but some of them at least. And therefore, the secretum of these glands can wash away bacteria which might be present in the crypt. So that's another factor which lowers the chances for inflammation in this tonsil, because similar glands are not nearby to the palatine tonsil. Okay? Okay, so these are the differences. Look at this other part of the tongue. It is given by these structures. What are these? This is visceral striated muscle. Okay? From here to there, because, or from here to there. Nuclei are always at the periphery of the muscle fiber. So be prepared to any question regarding muscle, because it is just here. You cannot escape. And it is not just to scare you or to give you questions what you cannot answer. This is just a natural thing. If something is in the section, why not ask once you have learned it? Okay? So this is the general tendency. So yeah, okay, so these are the specific features. Let's talk about the common features of tonsils. I enlarge this palatine tonsil. So in all tonsils we have lots of lymphatic nodules. Most of them are secondary, as you can see. So they are mostly the germinal centers, the pair territories. So these lymphatic nodules are of course B-dependent, but the interfollicular territories, so territories in the lymphatic tissue between lymphatic nodules, so interfollicular territory, it is T-dependent. T-dependent. And usually tonsils are surrounded by some connective tissue, but definite connective tissue capsule is found only around the palatine tonsil. So this amount of connective tissue, what you can see here, is something what you can already call a capsule. Right? And another thing, that high endothelial venules are present mostly in the interfollicular territories, which allow homing or extravasation of lymphocytes. So if you are asked to show high endothelial venule in a tonsil, you should go to interfollicular territory to increase your chances. So I do so. And look at this. This is a very nice high endothelial venule. You can see red blood cells in the lumen, and at the border of the lumen you can see these cuboidal euchromatic nuclei, okay, which are the endothelial cell nuclei here. So this is a typical nice high endothelial venule. Okay. So these allow migration of lymphocytes through the wall. Now, this side is the oral cavity, and at the border there is a lining epithelium, and the typical lining epithelium of the oral cavity is this: certified squamous non-keratinizing epithelium. So what you can see here, this epithelium is the epithelium mucosae around the oral cavity. And underneath we have the lamina propria, connective tissue. But there is no muscularis mucosae, okay? So this is an incomplete mucosa. And these lymphatic nodules actually appear in the lamina propria. But from this lamina propria, there is a high tendency of lymphocytes to migrate into the epithelium, what you can see here. This is already the crypt, so this is the lining epithelium of the crypt, which is continuous with the lining epithelium of the oral cavity, of course, okay? But if you look at this lining epithelium next to the crypt, it is not really looking like a very nice epithelium. Maybe here these upper 3/4 arrows, but below, the epithelial tissue is invaded by lymphocytes very much. So lymphocytes infiltrated the epithelium, you can say it that way, infiltrated or invaded. And they change the morphology of the epithelium so much that it is almost unrecognizable. That's why this kind of epithelium, which already invaded by lymphocytes very much, is called tonsillar epithelium or reticular epithelium, tonsillary epithelium, because these are typically in the tonsils. So such a heterochromatic round nucleus here, 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 they cannot be epithelial cell nuclei, because typical epithelial cell nuclei in the certified squamous non-keratinizing epithelium look like these. Okay, so these are lymphocytes, which are coming from the side of the lamina propria. And monitor the antigen environment of the epithelium, because antigens may arrive from the side of the crypt or from the side of the oral cavity. And trigger inflammation in the lamina propria, therefore transformation of post-capillary venules to high endothelial venules, which allow extravasation of lymphocytes. Lymphocytes gather here, and sooner or later B lymphocytes get activated, germinal center forms, and the whole process starts, what we already discussed. And at the end of the process, either B memory cells or plasma cells are formed. If the B cell could recognize the antigen with high probability. If they couldn't, then they die via apoptosis and build phagocytosed by macrophages. So the usual process what we have described in relation to the lymphatic nodules in the large intestine. In all lymphatic nodules, the very same processes are going on, indifferently of the location. Okay? So that's it. Yes?
Is there any consequences if there is one
Well, it is usually recommended to get it removed if you have a very frequent inflammation. And the reason is that the experience is that if somebody's tonsils, palatine tonsils, is inflamed frequently, and there is a slight inflammation always on, more or less continuously, because of these inflammatory processes, the patient will have higher chances for inflammation in the heart, which is much more dangerous. Yeah. Another thing, well, of course, so this is the advantage if you get it removed. You reduce considerable chances for your heart to get inflamed. Obviously, there is a slight disadvantage in terms of immunology, but we have other tonsils around, so it is usually not a problem. Waldeyr's lymphatic ring, have you heard about this? Jesus. Waldeyr's lymphatic ring. Have you had the second lecture in lymphatic organs already? I think it's there, or in the first one. I could see the slide. Unlike you, I regularly check the lecture slides. Okay, so have a look. Did you find it? Oh, my friend. And which slide? Number of slides? 6. Say it others. I already found it. So, surprise, surprise, how many things are on lecture slides. Okay, now, yes, one more thing I would like to not show, but say in relation to these scripts. So, sometimes if somebody has a very severe inflammation in his palatine tonsil, yellow spots appear on the surface. Those yellow spots are actually reflect presence of pus. P-U-S, do you know this word? Which fills up the crypts, but fills up entirely. And therefore, because the pus fills up the crypt entirely, the surface of the pus appears on the surface here and becomes visible if you just look into the oral cavity. So if these spots are present, it is an indication that the amount of pus is so big already that pus already filled up the entire system of the crypts. So it's a severe inflammation. Pus is a fluid which is mostly given by dead pathogens and dead immune cells. So there is a war in the crypt between immune cells and the pathogens, and both groups die, okay, and get disintegrated, these cells, and this kind of mixture is what we call pus. So that's an indication of a severe inflammation.
So for tonsil stones, what's that happen?
Tonsil stone.
Yeah.
Saliva stone, what I have heard about. Tonsil stone.
I'll show you afterwards.
Okay. So saliva stones are something what I have heard about. Concentration of molecules in the saliva filled up with salts, so form rigid structures, which can form a plug and restrict movement of saliva or secretum of glands towards the oral cavity. So it may lead to inflammation in this area, which sometimes look very frightening because it can be mixed up with enlargement of lymphatic lymph nodes in the neck area. But it can be just not an enlarged lymph node, but an enlarged territory where the secretum of salivary glands accumulated because they couldn't flow on towards the oral cavity because of the presence of the stone. I had one in the past. So it was a size of a green pea. So it's 3 or 4 millimeters round structure. It requires a small surgery in the oral cavity to remove. Well, it is small if it's already close to the oral cavity. If it is not, then it is more dangerous here in the neck region because we have so many things here. So I didn't get it done until it moved towards the oral cavity, so from the oral cavity it could be removed. Okay. Can we go on? So we have the spleen in 2 versions, and the only difference between the 2 versions is the color. And the intensity of color is different because although both specimens are from washed spleens, but one of them was more intensively washed. So what does it mean, washed spleen? So when the spleen, so first of all, the spleen contains lots of blood. In certain animals, for example in horses, that's a major function of the spleen to store blood. In humans, this is not a major function, but in horses, for example, it is. But even in humans, we have lots of blood inside the spleen. And if you remove the blood, remove the spleen and cut it and look at it with your naked eye, it is looking very bloody, very, very reddish. And if you create a section from a specimen like this, the many blood cells tend to cover the actual histological structure of the spleen. So that's why to create a meaningful histological section, which allow studying of the splenic histology, you need to wash away at least some of the blood from the cut surface of the spleen. So this was done by just water. But in one case, it was washed more intensely, so more blood cells were washed away. In the other case, less blood was washed away. And the reason is that certain structures of the spleen are visible better in one of these specimens, and certain other structures are better visible in the other one. So that's why I open both. Yeah. Okay. So let's start with this 24. This is the less intensively washed version. That's why it is darker, because more blood cells are present, which give the color mostly. If I enlarge this 24, you can see here on this surface the capsule. Okay, other edges here and there are artificially cut. So this is the only natural surface which is covered by the capsule. So this is an encapsulated organ. And there are connective tissue trabecules which arise from the capsule. And if you look at the color of this connective tissue capsule and these trabecules, you can say that it is rather pinkish than reddish. So you can say light red. And being this is a hematoxaniosin stained specimen, what your conclusion could be from this color? Yes, it is rich in elastic fibers and less rich in collagen. Okay. Why is this important functionally? It is important because this is related to the blood storage capacity of the spleen. It is stored there because that amount of blood creates a reserved part of blood, which is currently not in systemic circulation, but it can be pushed into the systemic circulation quickly by contraction of the capsule of the spleen. So, because it is contracting and then relaxing, some elasticity of the capsule is needed here. All right. Have you ever been have you ever experienced an unpleasant, very focal pain at the side of your spleen when you went for running, for example, without doing so for a prolonged period of time? So that's a kind of struggling of your spleen to push more blood into systemic circulation to meet the increased requirements, oxygen requirements of your muscles while you are running. Okay, so the same is happening in horses, but in much more pronounced manner when horses are running. Okay, but even in humans we can feel this. Okay, so elasticity is needed, but for contraction active elements are also needed, and they are these cells in the capsule, which look like smooth muscle cells, but they are not. They are myofibroblasts. So kind of cells which can contract, so similar to smooth muscle cells in this way, but they are also similar to fibroblasts because they can produce the extracellular molecules for the capsule, including molecules which form fibers. So that's why we call them myofibroblasts, contractile fibroblast-like cells. And contraction of these cells is responsible for the squeezing effect, which can pump additional blood to systemic circulation. Now, another thing, that on the surface of the capsule, in certain locations, not everywhere, but for example here, you can see squamous heterochromatic nuclei, which represent mesothelial cells here, which belong to the peritoneal coverage. This is an intraperitoneal organ. So this is sign of the peritoneal coverage. Well, in other locations we lost the mesothelial cell layer during sectioning, but here we are lucky. Okay. So below the capsule we have the parenchyma, but we use a special term for the parenchyma in case of the spleen, because in this organ we call the parenchyma as pulp. So So the pulp is nothing else than the parenchyma of the spleen. You cannot use this term in case of any other organ, only in case of the spleen. And the pulp has two major parts. White and red pulp can be distinguished. So these colorful names come from the colors, what you can see with your naked eye in an unstained specimen, a gross anatomical specimen. If you cut the spleen and look at it, you will see more reddish and more whitish looking territories in a freshly removed spleen at least. And the reddish territories are red in this case because of the presence of lots of red blood cells. And the whitish territories, what you can see with your naked eye, represent lymphatic tissue. Lymphatic tissue is whitish without artificial staining. Okay? And now, after hematoxylin staining, the red pulp is reddish because red blood cells still remain reddish. But the white pulp, so the lymphatic tissue, has a bluish appearance because of the many nuclei of cells, mostly lymphocytes. Okay? And you can see that the majority of the pulp is given by red pulp. In a healthy spleen, it is about 80% of the pulp. Okay, so let's talk about the white pulp first. It has three major subdivisions. One of them is the set of lymphatic follicles. So here these structures, like this, or like that, these spherical structures are lymphatic follicles or nodules, B-dependent territories. Usually they have germinal center. And they have the very same processes inside what we have already described. But in many cases, extrinsically, so at the side of the nodule, you can see an arteriole like this. This arteriole is called central artery. It's really an arteriole, but the name is central artery. And central artery. Don't confuse with central vein, which is in the liver, in the middle of the classical hepatic lobule. Students already mix them up, in my experience, during exams. It's a problem. Okay, both are correct. As I said, it is regarding size and arteriole, but in many books, let's put it that way, you will see central artery rather than central arteriole. We probably deliberately modified it to be arteriole to emphasize that this is relatively small. Okay. And lymphocytes surround this central artery. So that's why I call it central, because it is at the center of something. It is not in the center of the nodule, but in the center of something, what we call periarteriolar lymphatic sheath, or pulse, P-A-L-S, periarteriolar lymphatic sheath. Of course, you cannot pinpoint the border between the pulse and the lymphatic nodule, but somewhere in between. But functionally, there is a clear difference because the pulse is a T-dependent territory, unlike the follicle. So majority of lymphocytes in the pulse is T lymphocytes. And T lymphocytes undergo antigen-dependent maturation there. So they're T-cell receptors tested. Of course, in the past, therefore, there are interdigitating dendritic cells. There are also macrophages, which are professional antigen-presenting cells. Okay, So this is the pulse. Now, the third pulse is also part of the white bulb. The third part of the white bulb is called PAMS, periarteriolar macrophage sheet. PAMS. And to understand this, I need to show you a drawing. Because in the section it is difficult to show. Although maybe in the handout we managed to present some illustration. But I would rather like to show you these drawings. Which is about the blood circulation of the spleen. So this grayish something is a trabecule inside, and this is part of the capsule. So blood arrives to the spleen via the splenic artery, and its branches going inside the trabecule, and those may be called as trabecular arteries, therefore. Branches of these trabecular arteries may leave the trabecule, like this reddish something. This is the central artery, branches of the trabecular artery. The blue structure around the central artery is the pulse, what we just referred to. Pulse. Now, the central artery may continue as penicilliform artery. Which is called this way because the morphology of these little arterioles resemble the hairs of a brush, what you can use for painting. So that's why it is called penicillar artery or penicilliform artery, referring to the resemblance to the brush. And some of these at least, some of these penicilliform arteries are surrounded by lots of macrophages, which is represented as these green structures. So this is the periarteriolar macrophage sheet. A macrophage-rich territory around the penicilliform arteries. All right? So this PAMS is the third part of the white bulb. So we have follicles, we have pulse, and we have PAMS. All these together give the white bulb, correct? The lymphatic tissue. So one function of the spleen is to help antigen-dependent maturation of B and T lymphocytes as well. Because we have B and T dependent territories as well. Now, another way how this central artery may continue, that it may form capillaries which are just responsible for supplying follicles with nutrients and oxygen. And there is a third way how the central artery can continue. This third way is just to open freely into the red pulp without any continuation of the endothelial lined vascular system. Alright. Therefore, this kind of circulation is called open circulation. If blood directly goes to the red pulp from the endothelial lined vessel. And contrarily, if this doesn't happen and blood is going through the spleen within an endothelial lined vessel system, that is the closed circulation. And if blood flowing through this way, then it will not go directly to the red pulp, but will continue into splenic sinuses. Splenic sinuses. which are kind of venous sinuses. Now, and this is when I need to show you the other section where these structures are better visible. But they are visible in the other one as well. So here, red pulp is the territory, the remaining part of the parenchyma, which is not follicle, not pulse, not pumps. And in the red pulp can be divided into two subparts. A collection of sinusoids, like this, or like this, which are blood vessels, sinusoids. And the territory among these sinusoids, which is called splenic cord, system of splenic cords. So sinusoids and splenic cords are the two parts of red pulp. And let's look at the wall of this sinusoid. You can see these round nuclei around. Actually, those are endothelial cell nuclei. They are elongated, but they have the cross-sectional profile, what we can see. And the wall is extremely thin, as you can see. And actually, the whole structure of a splenic sinusoid is very unique, and this is illustrated in this drawing. This is a very special discontinuous endothelium, what we have in the splenic sinusoids. You can see these elongated gray structures, one of which is blue. These are the endothelial cells in the wall of the sinusoid. This blue one is just one endothelial cell, so they are really elongated. But in cross-section, what we could see before, it looks round. And there are gaps between endothelial cells, as you can see. That's why we can call it discontinuous endothelium. Now, these red structures here are macrophages, whose processes may go through the gap, and therefore the processes of macrophages may be inside the lumen of the sinusoid, so in direct contact with blood. And this represents one other major function of the spleen, which is filtering of blood. And these macrophages monitor antigens in blood and phagocytose them. So they just pick up the antigens. So this is an analogy here, because spleen, one function of the spleen is to filter blood. But one function of the lymph node is to filter lymph. Because in the sinusoids of the lymph node, we have lymph, but in the sinusoids of the spleen, we have blood, and not vice versa. If you say otherwise, that's a major problem, because you don't understand one of the major functions of these organs. Do you understand the problem your examiner faces when you state it differently? Okay. There is another thing here in this drawing, these green structures, which are reticular fibers, which surround the endothelial cells. But there is no continuous basement membrane here, no basal lamina at all, just scattered reticular fibers around the endothelial cells. So this is a special, very special discontinuous endothelium. But the whole structure, what you can see on the drawing, is very much the same as the structure of a barrel. So in a barrel we have those wooden elements, those wooden pieces called staves, I think, staves. And these wooden elements, building blocks of a barrel, are surrounded by round metallic so-called hoops, okay, looping around. Now, the staves, the wooden elements, correspond to the endothelial cells, and the hoops, the metallic wires around the elements of the barrel, correspond to reticular fibers. Okay?
Professor?
Yes.
So, the green one is the hoops for the bottles. I didn't understand.
This whole thing is a barrel. Barrel, what
Oh,
in which you can store wine.
okay.
And there are wooden pieces in the barrel, just like here we have endothelial cells. And metallic hoops around the barrel correspond to the reticular fibers which surround the endothelial cells. So this is an analogy. Okay, now, and we arrive at the third, not third, maybe, I don't know, another major function of the spleen, which is the elimination of old erythrocytes. Now, let's suppose that we have a red blood cell which is in the lumen of the sinusoid. If the red blood cell is young enough, it means that it can change its shape considerably because of the special skeleton of red blood cells, what we learned. So, if you have ear, you can already recognize that once during the spleen exam you arrive at this point, it is very natural to ask about the cytoskeleton of the red blood cell. Why is it special? So again, you cannot escape. The only solution just to hold everything in your mind, the whole material, because this is going to be tested during the final exam. Yes, it is tiring. Yes.
Can you repeat the question?
What is special in the cytoskeleton of the red blood cell which allows its deformation? I don't want you to answer this, but look after it at home. Spectrin, arginine. So special proteins in the cytoskeleton. Special intermediate filaments and proteins in the cytoskeleton. Okay, so young red blood cells can go through these tiny gaps between endothelial cells, right? And therefore they may end up in the red part, in the medullary cord. Okay? And reversely, they can also go back from the medullary cord, oh no, not medullary cord, splenic cord, sorry, splenic cord. From the splenic cord, they can go back to the sinus. But if a red blood cell is not very young, the cytoskeleton is more rigid, then it may be trapped in the splenic cord because they won't be able to go back to the bloodstream, right? And this is detected by macrophages which are in the splenic cord and phagocytose them. So this is the way how old erythrocytes are eliminated in the spleen. And the morphology of the splenic sinusoids, the special morphology, is needed for this process. Can you follow the logic? Everything is interconnected with everything else. I said it many times, I think. Do we really need this? know, there is a special button what I usually activate here, which mute these things. Instead the device will just vibrate or will not do anything. I would suggest to use that more frequently. Okay. If a red blood cell arrives through the open circulation, which means it arrives directly to the splenic cord rather than arriving directly to the sinusoid. That's also possible if you have open circulation as well. In certain animals, both kinds of circulations are present in the spleen. There is a dispute how is it in humans. Okay. But even if the red blood cell is arriving via the open circulation, so it is originally not in the splenic sinus, but it can go to the splenic sinus if it is young and can escape from being phagocytosed by the macrophages of the splenic cord. But if it is old, then it will be trapped in the splenic cord and macrophages will find them. What is the average lifespan of a red blood cell, by the way? 120 days. What is the immediate precursor cell of a red blood cell? Reticulocyte. And there are 4 before that. Embryology. Everything is interrelated with everything. Alright? This is awful. I know. It is awful. But it is getting better as you learn. Or okay. I can show you an electron microscopic image showing a cut splenic sinusoid. Can you see these elongated rope-like structures? Those are the endothelial cells of the sinusoid. Okay. This is and this M is a macrophage in the wall. Okay. EC endothelial cell. Okay. And let's look at the section again. Here in the splenic cord, you can see macrophages like this with reddish cytoplasm. Okay? But sometimes these macrophages, cytoplasm, has a brownish tint. Can you see here or there? And also remnants of something. Now this brownish tint is a substance called hemosiderin, which is the remnant of the red blood cell which had been phagocytosed by this macrophage. And in the macrophage, there is an iron-containing substance called ferritin. So hemosiderin contains ferritin. And generally, iron is present in the middle of the hemoglobin. So again, everything is interrelated with everything. All right. So this structure is a proof that erythrocytes are really phagocytosed by macrophages, as we described. Okay, so we are very good because just 1 minute before time we finished it. Can you ask something? Yes? Well, sphenic chord is everything which is not wide pulp and not sinusoid and not trabecule. So all this territory which is more rich in nuclei than the lumen of the sinusoid. Okay? Anything else? I don't understand. During exam? Well, usually, you will have how many? 2 sections, I think. And for one student, during histology exam, usually we don't spend more than half an hour with one student. Sometimes less, sometimes more. In my experience, there were examples where when I gave mark 5 in 5 minutes. But there were other examples when I failed a student after 1 hour, after 1 hour exam. Because even after 1 hour, he or she couldn't persuade me that he or she knows the material. And we just don't have time to allow students for one student. So it is slightly variable, but usually it's something between 20 minutes and 30 minutes for the 2 sections. Which is perfectly enough to convince me. If you focus on important things, point to it, this is that, this is the